Hello, 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 and welcome back to Shiksha DaCosta. Today we're going to learn about where we see linear systems in real life and how they're applied. As part of this lesson, you're going to learn how to spot a situation in real life where you say to yourself, hey, I bet a linear system can be used to solve this. And you're successful when you can actually solve those problems that arise from real world situations, if those are sort of described to you in words or if they're represented already to you by a linear system of two equations that involve two variables. And the way we're going to solve these problems is by choosing the best method to do so, whether that's algebraically or graphically. To start off, let's check out this problem here. Klaus bought a 3D printer for $12,800, and that's about the price that a commercial 3D printer goes for. And when Klaus prints his miniature figurines, it uses filament, and that filament costs 30 cents per milliliter. He then sells those miniature figurines for $5 each. Look at these guys, they're all $5. How long or when will Klaus actually break even if the average figurine contains 2 cubic centimeters of filament? There is a lot going on in this question, but pause the video here and take as long as you need to go ahead and solve it. Well, like most linear systems problems, well, we know it's a linear systems problem, but let's try to um, come up with some equations that might fit the situation and examine some of the relationships happening here. The first thing is we're asked, when will Klaus break even? What does this word or this phrase mean, break even? Well, to break even means when you are running a business, the total costs are equal to your total revenue. So basically, you have earned a lot of money, and that money is equal to pay off the cost of running your business. And in Klaus's case, he's got a lot of costs. The milliliters over here, the cost for the filament, well, it's sold in milliliters, but the figurine is measuring its volume in cubic centimeters. Thankfully, though, that conversion is just about as easy as it gets. A milliliter is a unit of volume that is equal to exactly 1 cubic centimeter. Now, if each figurine then contains 2 cubic centimeters or 2 milliliters, each one will cost about 60 cents worth of filament. So each figurine would cost 60 cents to produce. Now, Klaus's business also has an initial cost. He did spend $12,800 on the printer. And so if we want to find out how much Klaus is paid, how much his costs are for his business, well, that depends on how many figurines he produced. If he produces 0, he still has this much in his total cost. So Klaus's costs are 60 cents times the number of figurines that he actually makes. So we need another variable here. N is going to represent the number of figurines he makes and sells. We're going to multiply that by 60 cents to find out the cost for the filament plus the cost of the printer initially. And that will tell us his total cost. His revenue is much easier to calculate. The amount of money that he makes, well, that is $5 times the number of figurines that he sells. And since we're looking for the break-even point, we're asking the question, when does C equal R? When do his costs equal his revenue? Well, at this point, we can recognize that his costs are represented by this equation here, 0.60n plus 12,800, and his revenue can be represented by 5n. Now all we have to do is isolate n to find out how many figurine sales would it take for him to reach this break-even point where C is equal to R. To do that, let's isolate our constant here by moving this term over. We'll subtract 0.60n on both sides, and we're left with 12,800 equals 4.4n. And now we can divide both sides by 4.4 to find out that the value of n is about 2,909. Now, he cannot sell 0.9 of a figurine, so we do have to round this number. And unfortunately, 2,909 is not enough. That is, he needs to sell more than that to actually break even. So we would say that he probably needs to sell 2,910 figurines. At this point, if he sells 2,909, he's still running a loss. Now he's running a bit of a profit. Now, I solved this problem through substitution. But of course, that may not have been the best strategy. Once I came up with these two equations, it might have been simpler to simply use a graph. If I had a phone near me or a graphing calculator or anything like that, I could simply put in these equations and then look for the point of intersection. Which strategy you choose will vary pretty drastically depending on the type of person that you are. And it's important to know that that really all of the strategies are viable and some of them fit better to different situations. In this case, because the slope of one of them was so low compared to the other, graphing technology may have made it really difficult, especially because the y-intercept is all the way up here at 13,000. It might be very difficult to find out what the scale is that results in a nice graph where you can see the point of intersection. Then again, you may not have a piece of paper and a pencil on you to run through substitution, or even a calculator to do the division by the decimal. The situation calls for a different strategy every time. Linear systems frequently appear when we're trying to find some sort of optimal or balancing point. They're present when we're comparing service providers like home internet or phone, since those costs usually have a fixed amount plus a rate. So, for example, for internet, it might charge you $40 plus 5 cents per gigabyte. So, that per gigabyte would be the rate, and that $40 would be the fixed amount. And if you're comparing two different service providers, well, then you might be looking for a point where those two service providers actually cost the same amount of money. Linear systems are also present when we're finding break even points in business, like we just saw. And they are also present when we're taking two different mixtures and we're trying to find the ideal amount of each one to combine in order to reach a specific concentration of one of the ingredients that's in the mixtures. And that's a lot to parse right here, but we'll see a few examples of that. But there are so many more situations that call for us to use linear systems. The important thing when we are using them, though, there's two really key things that you should follow if you want to make sure that you don't end up confusing yourself, because there's a lot of things going on in these problems. First of all, when you are creating the equations, always make sure each variable is really well defined by using a let statement. So before you even say 3x plus 2y, what is x supposed to represent? What unit are you using? Number of something? Are you measuring things in milliliters or in centimeters or in dollars? And then once you are done the question, make sure you're writing a final statement that wraps this up, that closes the loop on this. Your final statement should include the units. It should be very clear how you're answering the question that's being asked. In this example, Klaus is mixing paints to find the very perfect shade of green to paint his miniature figurines, some of which you might be able to see here. He finds two paints that are being sold. One is at a 71% saturation point, so that's a lot of green dye in it, and one might be at 26% saturation, so that's quite light. He wants to make 200 milliliters of paint, and that paint needs to be at exactly 34% saturation. How much of each paint must Klaus buy in order to reach his goal? Pause the video here and see if you can figure that out. Well, before we can start solving a linear system, we actually need the linear equations, right? And to do that, we have to recognize what are the variables in this scenario. What is Klaus trying to do? Well, we know he's mixing these two paints, and he wants to figure out how much of each paint. So one variable might be the amount of one paint, the other variable might be the amount of the other. So let's label those. I'll say H is going to represent the amount of the high saturation paint, and that's 71%. And that's going to be measured in milliliters. I chose to use milliliters because he wants to make 200 milliliters of paint. The other paint, the low saturation paint, is going to be represented by L. and that is the 26% saturation. And that is also measured in milliliters. And we know that he wants to make 200 milliliters of his special perfect shade. And so if we take the amount of high saturation paint and the amount of low saturation paint and we add them together, however much we're using in our mixture, we need to get exactly 200. Now, what about the other equation? And this one is pretty difficult to come up with if you've never seen a problem like this done before. It sort of involves recognizing that there's amount of green dye in each of these paints. So if we take the amount of high saturation paint and multiply it by 0.71, which is 71% as a decimal, we'll sort of get an idea of how much green dye is being mixed inside here. And then if we very similarly take L and multiply it by 0.26, we'll find out how much green dye is here. And we know that in our final mixture, 34% of 200 milliliters needs to be green dye. That's what that saturation concentration sort of means. And that is exactly 68 milliliters. So if you didn't understand that, pause the video here and take a look and see what I mean, but I will repeat this one more time. So we're going to take the amount of high saturation paint and multiply that by 71%, which as a decimal is 0.71. We'll do the same with the low saturation paint times its percentage, and this tells us basically how much green dye is coming out of each amount. In total, we need 68 milliliters of green dye in our solution because that would be exactly 34% of the 200 milliliters of solution that we have. So those are our two linear equations. Now, how do we actually find out the amount of each type of paint? I've decided to tackle this problem with elimination, but certainly substitution could be one way that you go at it. You might graph it and look for the answer that way. You might even do that by hand. I'm choosing elimination because it's one of the ways that's a little bit faster for me. All I need is the same coefficient in front of one of the variables. And I'm going to say, let's try and eliminate h. So I'm going to take the first equation and multiply it by 0.71. The second equation, I'm just going to leave the way it is because 1 times 0.71 gives me 0.71. And now those coefficients are the same. And when I do equation number 1 minus equation number 2, those will cancel out. And when I subtract these, I end up with equation number 3, let's call it that, at 0.45 L should equal 74. If I divide both sides by 0.45, I find out that L, the amount of low saturation paint I need in the mixture, is 164.44 milliliters. Now that I found that, I also need to know how much of the high saturation paint I need, and I have an equation to help me with that. Using that first equation, all I'll do is I'll isolate H, and now I'll replace L with its actual known quantity. Now there's a little bit of a tricky thing happening here. Whenever you're replacing a variable and you have a really long number stored in your calculator, notice that I didn't round this number. I put these 3 dots to indicate to myself that there are more digits here. And I won't use this version of the number over here. I won't use the rounded version. I will just use the answer button on my calculator. So on my calculator, I'll type in 200 minus answer. Look for that button on your calculator because you will certainly need to use it when the math gets pretty complicated like this. What this does is it just takes the last thing that your calculator actually calculated. 74 divided by 0.45. Your calculator should have told you that that's 164.44444444. Now if you type in 200 minus answer, it will take that exact number that was given to you before and subtract it from 200. Your calculator may even show you 10 digits. There are more than 10 digits in this number, and it is storing all of those digits in its memory. And it's going to use all of them in this calculation. So we do end up with 35.555555, and again, there are many, many more digits here. It's always a good practice to never round any numbers in your math problems until the very last step, which is where we are right now. We were looking for how much of each paint he must buy, and it looks like he needs to buy about 164 milliliters of the low saturation paint and about 36 milliliters of the high saturation paint. I rounded these to the nearest whole because the question didn't quite tell me exactly how many decimal places to round to, but I figured it'd probably be very difficult for Klaus to get an accuracy, a degree of accuracy that's stronger than 1 milliliter. And so that's my answer for this question. Hopefully, Klaus is able to find that perfect shade of green that he's been looking for. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.